Okay, so let us now again start with the shortcuts on wave optics. In the last lecture, we have calculated the intensity distribution for the fringes in Young's double slit experiment, and we have seen that the intensity distribution is given as I is equal to 4a square cos square phi by 2, where a is the amplitude of two waves and phi is the phase difference between two waves. And when I draw the pattern, I will get the fringe intensity distribution like this. In the last lecture, by mistake, I have written here 2 pi. But at 2 pi, when phi is 2 pi, we'll get a maxima. So I will get a minima at pi, and then at 2 pi, I will get a maxima. So please kindly note that. Now, we are going to see that when do we get maxima and minima. Before going to the conditions for maxima and minima, let us understand a wave. For example, if I take a wave which is starting from here and going like this, then lambda is the wavelength for the wave. Now if I take another wave which is again starting from here, so basically both the waves are in phase. If I speak in terms of the phase difference, then if I superimpose this wave B on A, then they will add constructively. Similarly, if I have a wave which has a path difference of lambda, I start from here and then I name it as C. So if I superimpose wave A with C, then what will I observe? That again, when they superimpose, both the waves will superimpose constructively. Similarly, if I have two waves with path difference 0, lambda, 2 lambda, I can also start a wave from here. Then both the waves will superimpose constructively. So what do we infer from here? That if the path difference is integral multiple of lambda I get constructive interference. Now, if I take a wave which is completely out of phase, for example, like this, and then if I superimpose wave A and D, then I will see that both the waves, they will superimpose destructively. Here it is completely out of phase. The path difference is lambda by 2. Similarly, I can also have a wave with a path difference of 3 lambda by 2. Then the waves will superimpose destructively. So I get the inference that if the path difference is odd multiples of lambda by 2, then I will get destructive interference. Is odd multiples of lambda by 2, I will get destructive interference. So now I can say that for constructive interference, I can make a general statement. In any experiment, if I would like to see the constructive interference, the path difference should be integral multiples of lambda. And for the destructive interference, the path differences should be odd multiples of lambda by 2. Now these are the general statements. Whatever experiment I do, I can find what are the conditions for constructive and destructive interference by finding out the path difference. So the most important quantity which we require to find in any experiment in order to understand the interference phenomena is the path difference. Now let us calculate the path difference at P in Young's double slit experiment. Let us take again two slits, S1 and S2, and the two waves from S1 and S2, they interfere at P. Now we need to find, let D be the distance between two slits and capital D be the distance between the source and the screen. Two slits and capital D the distance between source and screen. Now the S1P ray, S1P is diffracted at angle theta. So I can draw it here like this. This is angle theta. Now I want to find the path difference between S1P and S2P in order the path difference between S1P and S2P in order to find the conditions for maxima and minima in Young's double slit experiment. In Young's double slit experiment. Okay. Now we can also see these two waves emerging from S1 and S2 as parallel rays. This I can say because the distance between two slits is very small as compared to the distance between the source and the screen. So I can take an approximation that S1P is parallel to S2P. Now in order to find the path difference between these two waves, if I can drop a perpendicular from S1 onto S2P, and I can mark this as M. So my path difference, which I denote by delta, this is equal to S2M. Now I need to find the mathematical expression for this. From here I can see that already I told you S1P is being diffracted at angle theta. Now this full is 90, so my this angle will be 90 minus theta, and again this angle would be theta. So the path difference S2M, this is equal to, if I write in terms of d and theta, from triangle S1 S2M, I get S2M as d sine theta. This is my path difference for Young's double slit experiment. Now I know that for constructive interference, the path difference should be integral multiples of lambda. So I can write for constructive interference d sine theta is equal to n lambda, where n is equal to 1, 2, 3, and so on. We can also take here 0, because when path difference is 0, again we will get the, at the center we'll get the maxima. So this is my condition for constructive interference or bright fringes. For destructive interference, we already saw that the path difference should be odd multiples of lambda by 2. So I can write d sine theta is equal to 2n plus 1 lambda by 2, where n is equal to, again I can take 1, we can start with 0, 1, 2, and so on. This is my condition for the destructive interference. So whatever experiment you do, you just need to find the path difference, and then the general conditions will hold true. You can straight away write that the path difference, if it is integral multiples of lambda, we get bright fringes, and if the path difference is odd multiples of lambda by 2, you'll get dark fringes. Now we will try to locate the fringes in Young's double slit experiment with the help of our conditions of maxima and minima. Again we have here two slits, the same diagram. Now I'm denoting these two waves by points A and B, and these two waves are superimposed at point P. Let us take the distance between two slits as D and locate the fringe at P from the center O at distance x. We need to find this x in terms of known parameters d and theta. Now again this is my angle theta, and this will again be theta, and then from here, from this rectangle, I can write, if this is O, my CO will be d by 2, OD will again be di2 by symmetry, and then if this is x, then PC will be x minus d by 2, and PD would be x plus d by 2. Now we will try to locate the fringes. Let us take triangle A, P and C and triangle B, P, D. In triangle APC, by the use of the Pythagoras theorem, I can write AP square is equal to PC square plus AC square. PC is the distance between source and the screen is D. So I can write here as D square plus AC, sorry, this is my AC square, and here I can write PC square. It's the same thing. PC would be x minus d by 2. Now in triangle BPC, again using Pythagoras theorem, I can write BP square is equal to d square plus x plus d by 2 whole square. Let us mark this equation as 1 and this equation as 2. Now from equation 1 and 2, let us find out BP square minus AP square. Why I am interested in this quantity? Because this quantity will give me the path difference. Let's see. So I will get d square plus x minus d by 2 whole square minus d square plus x x minus d by 2 whole square. When I calculate this, you can just expand the squares. D square will cancel from here, x square will cancel from here, then d by 2 whole square will cancel, then I will get only the term from here xd and a term xd from here, and finally I will get 2xd. So bp square minus ap square is equal to 2xd. I can write this as bp minus ap and bp plus ap. This is equal to 2xd. Now, because the distance between two slits, again I can use the same approximation, that the distance between two slits is very small compared to the distance between the source and the screen. D is very small compared to D, so I can take my rays parallel S1P is parallel to S2P, and or AP is approximately equal to BP approximately equal to D. So here I can substitute BP minus AP, and this I can take approximately as D, and this also approximately as D. So I will get 2 capital D, this is equal to 2xd. And here, from here I will get AP minus BP minus AP is equal to xd by D. What is this? This is my path difference between BP minus AP. Now, for constructive interference, or by bright fringes, this path, this is my general equation. Bright fringes, this path difference is n lambda. So I can write xd by capital D is equal to n lambda. Here I can denote xn, or xn is equal to n lambda d by D. This is my position of nth maxima, where I can write n is equal to 0, 1, 2 and so on. For dark fringes, the same path difference I can take as odd multiples of lambda by 2, or I can get the position of dark bands as 2n plus 1 lambda capital D by 2D, and so on. This is how we can locate. So from this expression it is clear, if I take n is equal to 0, then xn is equal to 0, the central fringe will be bright, then the next bright fringe will be at distance lambda capital D by small d, and so on. So we'll get alternate bright and dark fringes. Now, one most important thing is left to calculate is the fringe width. What is fringe width? The distance between two consecutive maximas or minimas. This fringe width expression will help us to understand that how our fringe width or how our interference pattern will change. For example, if I change the wavelength of light used, or how it will affect if I change the distance between two slits, or the distance between the source and the screen. So this fringe width I can find by finding the distance between two consecutive maximas, and this I denote by beta. So I can do that x n plus 1th maxima minus nth maxima. So I can find this as, I know the expression for this, n plus 1 lambda d by d minus n lambda d by d, and I will get lambda d by d. This is my expression for the fringe width. So what do I understand from here? Same, if I calculate the distance between two minimas, I will get the same expression. So please check for that. Now from this expression, what do I infer? If I change lambda, for example, if I'm going from red to yellow light, then going from red to yellow, lambda decreases. So from this expression, beta also decrease. Similarly, if I decrease the width of the slit, the distance between two slits, then my beta will increase. So I will have a more broader pattern. This is what we expect from interference fringes, that as we reduce the width of the slit, we get a better interference pattern, but still there is a limit. So similarly, if I increase capital D, then again beta will increase. So these are some important results we get from this expression, and we can understand the interference pattern more nicely. Okay, so I'll stop here. In the next lecture, we'll try to understand the interference happening from other phenomena. Thank you.